Hello, and welcome to the Chapter 8 Selected Problem Solutions video. In this one, we're going to work through some problems in Chapter 8. I've indicated in the comments or in the description of the video which problems I go over, along with timestamps for when those problems begin. That way you can just pick and choose where you want to start this video, or you can listen to the whole thing if you want. So we're going to start here in section 8.1, problem number 8. In this one, each student is given a 6-digit code, and we want to know A, how many different codes are there? Just how many codes total. In part B, we want to know how many codes are the same forward as backwards. How many codes are the same forward, backward, so that if we read it forward, we get the same thing as when we read it backward. So symmetric codes. Part C, we want to know how many codes contain only odd digits. And part D, we'd like to know how many codes contain at least one even digit. All right, so let's get cracking on this one. How many codes? How many total codes? Well, all right, so our 6-digit code looks like 1, 2, 3, 4, 5, 6, where these blank spots can be a digit, 0 through 9. And so each spot, there are 10 options. So there's 10 options for this one, 10, 10, 10, 10. So this is like a permutation with repetition because order matters and we are allowed to repeat digits. And so this gives us 10 to the 6th or 1,000,000 codes. How many codes are the same forward as backwards? Well, let's try and do it the same way we did that one. 1, 2, 3, 4, 5, 6. And we'll just start going through. So there's 10 options for the first one, right? 0 through 9. 10 options for the second one. 10 options for the third one. How many options for the fourth one? So like think of an example here. So 1, 2, 3. How would I make a code that's the same forward as backwards? Well, now I would have to go 3, 2, 1. So that it goes 1, 2, 3, 3, 2, 1, 1, 2, 3, 3, 2, 1. Forward is backwards, same. And so when I get to this fourth digit, it has to be the same as this third digit. And so there's only one option for that. There's only one option for the fifth digit and only one option for the sixth digit. So I get, so exactly half of the codes, or sorry, not half of the codes, 10 to the third codes are the same forward as backwards. All right, how about only odd digits? So let's figure out what are our odd digits. So the odds would be 1, 3, 5, 7, and 9. So there are 5 total odd digits, and then we can go the same thing. 1, 2, 3, 4, 5, 6. Okay, and so there's, let's see, then we have 5 options for each slot. So 5 times 5 times 5 times 5 times 5 times 5. So that's 5 to the 6th. All right, how about at least one even digit? So what we're going to do, the strategy for this is we're going to count how many have no even digits. So if we count how many have no even digits, then, and we already know how many total codes there are, right? 10 to the 6th. So the remaining ones must be the ones with at least one even digit. How many no even digits? Well, that's all odd digits. That's 5 to the 6th. We already solved that one. And so the answer to our question here is at least one even digit would be, well, we'll take total number of codes and subtract off the ones with no even digits. So 10 to the 6th minus 5 to the 6th. And so we can think through those like that. In each case, we use the multiplication principle. Didn't have to use addition principle too much there. All right, let's move on. All right, 8.2. How many 8-bit strings begin with 1, 0, end with 0, 1, or have 0, 0 as their middle 2 digits? So I'm going to draw a blank 8-digit string. And let's see here. So How many 8-bit strings begin with 1 0, end with 0 1, or have 0 0 as the middle digit? So it seems like we have choices here, and so let's divide these into sets. So I'm going to let A be the set of all strings that begin with 1 0. I'm going to call that A. The ones that end with 0 1, I'm going to call that B. And the ones that have 0 0 as the middle digit, I'm going to call those C. So these sets are going to contain the codes that satisfy those criteria. So why do I do that? Well, that's to better sort of explain what's being asked here, right? We're not looking for 3 different numbers here for the answer. We're looking for what's the total number of 8-bit strings that satisfy one of these 3 conditions. That is, what we want to know is we want to know what's the cardinality of A union B union C. Begin with 1 0, or end with 0 1, or have the middle 2 digits as 0 0. And so this becomes a pigeonhole problem, right? Well, we are in not a pigeonhole problem, a principle of inclusion-exclusion problem, because we are in 8.2, and so it makes sense that that should appear here. And so let's write out A union B union C then is, all right, so add up the cardinalities of A, B, and C, subtract off the intersections of 2, and then add in the intersection of all 3. All right, so A would just be how many 8-bit strings begin with 1 0. So that means these 2 are predetermined, and the rest, we have 2 options for each case, right? So that's 2 to the 6th. So cardinality of A is 2 to the 6th, and actually the same reasoning should apply to B too. If it ends with 0, 0, 1, these 2 are predetermined, and the rest are degrees of freedom, and there's 2 options for each slot, so that's 2 to the 6th as well. So, and same thing for the ones that have middle digit 0, 0. So for all of these, we'll have 3 times 2 to the 6th. Each one was 2 to the 6th, and we had 3 of them. How about the doubles? So if it begins with 1 0 and ends with 0 1. So if it begins with 1 0 and ends with 0 1, well then those 4 digits bits are predetermined, and so we just have 4 degrees of freedom, hence there's 2 to the 4th. A similar line of logic will tell you there's 2 to the 4th in each of these pairs, each of these intersections of 2 sets. And so that's going to be minus 3 times 2 to the 4th. And then what if it has all 3? Well, I'll stick a 0 0 here. So this would be a string. This is an example of a string in A intersect B intersect C. And notice we have 2 degrees of freedom. So that's 2 to the 2nd. So plus 4, 2 to the 2nd. I'll let you calculate that and come up with the answer on your own now that we have a formula for it. So that's how we can approach a problem like this. Remember the ORs telling us we're talking about a union, we're counting a union of sets. We would normally add, right? If they were disjoint sets, we could just add the cardinalities, but here there's some overlap. And so we have to make sure to take care of that overlap by using the principle of inclusion-exclusion. All right. Let's try number 14 here. Another principle of inclusion-exclusion one, 8.2, number 14. 28 people like Chinese food, 23 like Italian food, 35 like Mexican food, 15 like Chinese and Italian, 20 like Chinese and Mexican, and 12 like Italian and Mexican, and then 9 like all 3. We want to know how many like at least one. And so this is a straight principle of inclusion-exclusion one. So I'm going to call the people that like Chinese food, I'm going to call that set C. Italian food, I'm going to call that set I. And Mexican food, I'm going to call it M. And so the people that like Chinese and Italian, well, that would be the intersection of C and I. Chinese and Mexican, intersection of C and M. Wait a second. Back it up a second. They like Chinese. Yeah, no, this is good. Yeah, that's what I want. C intersect M. And then Italian and Mexican, I intersect M. And then all 3, well, this would be I intersect M, intersect C. So these are telling me cardinalities of these sets. So this is 28, 23, 35, 15, 20, 12, and 9. So I have it pretty well set up right now to use principle of inclusion-exclusion to get how many like at least one, because how many people like at least one? Well, that's asking for the union of all of these sets. How many people have selected at least one of these things? And so we can calculate that with principle of inclusion-exclusion. So this is all the individuals minus the intersection of any two. And then add in the intersection of all three. Oh, not A. And then add in the intersection of all three. So I intersect M, intersect C. So this is 28 plus 23 plus 35 is 15 minus 20 minus 12 plus 9. Let's add them all up. Figure out what we got here. 28 plus 23 plus 35 minus 15 minus 20 minus 12 plus 9. Total of 48. So 48 people liked at least one of these kinds of food. Okay, how many people like exactly two? So there is a formula we could use for this if we just want to get the twos. There's a couple ways we could do this one. In the discussion post, I saw a couple people actually recommend the strategy is just like build up from the intersection of all three. Like think about it piece by piece. So I think what they were getting at here is, here I'm going to draw my Venn diagram of the situation. And I'm going to label these Italian, Mexican, Chinese. So I know that there's a total of, 23 people that are going to go in the I, accounting for all the different sections of I. And same for M, there's 35 there, and there's 28 here. I'm just going to put it on the outside right now. And what I'll put in this part here for each one of these is just the ones that liked only that option. So, and that'll just be the ones that like Chinese food and none others. So I'm going to utilize all the sections here. And so we can't go right to that. We need to start really in the middle. So we know there's 9 people here. Let me zoom in on this. That's a little small, huh? So there's 9 total people in this tiny intersection, the intersection of all three. And so then I can work backwards from that. So I know there's 12 people in the intersection of Italian and Mexican. So Italian and Mexican, that's these two. How do I do this with the colors? That's this area here. That's that. All right, I'm going to undo that. And so I know there's a total of 12 in that. And so there must be 3 in the other part of that intersection, right? So there's got to be 3 in here. That way there's 12 in that intersection. All right, Mexican and Chinese food, there should be 20 in there. There's 9 in the intersection of all three. That means there must be 11 here. Italian and Chinese, there's 15, and so there must be 6 people here. And now Italian, I have 23 total, and how many are accounted for already? 15, 18, so that must mean there's 5 out here. Actually, I could stop right now, but we're going to fill out the whole picture in case you need that for like an exam or something like that. There should be 35 total people that like Mexican food. There's 23 there already. And so what's that? 12 here. And then 28 here, that's 20, 26. That means there's just 2 people here that like just Chinese food. And now we can answer the question of how many people liked exactly 2. That's this guy, this one, and this one. So we should get a total of 20 people liked exactly 2. And there you have it. So that's how you can backtrack. That's how you can backtrack from the intersection of all three. I guess while I'm at it, why don't we show the other method for how you might do this in case maybe you want a formula in general. So we'll do it like how we proved the principle of inclusion-exclusion for 3 sets. So I'll draw my 3 sets, and remember, I just want to count the ones that I counted over here, right? Just in the intersection of 2 and not 3. So if I add cardinality of A, cardinality of B, cardinality of C, I will have counted 1 here, 1 here, or sorry, 2 here, 1 here, 2 here, 1 here, 2 here, and then 3 in the middle. That's how many times I would have counted the elements in each section here. So if I just want, yeah, how can I do this? If I want to peel off, maybe I don't want to start with that. Maybe I don't want to start with doing cardinality of A, cardinality of B, cardinality of C. Because how am I going to get rid of those 1s? Make it a little bit bigger. All right, we're figuring this out as we go, guys. So, okay, what if I deal with just the intersection? So let's say we add this intersection in, so we've counted that each once, and now let's add in this intersection, so this is going to turn into a 2. And now let's add in this intersection here, 1, and then I'll get a 3 here. I've counted the middle 3 times, and so it looks like if I just pull off that middle section thrice, I will get the ones that will like exactly 2. And so what did that look like? So exactly 2 sets. Let's call this A, B, C. Doesn't really matter, but exactly 2 sets. What did we do there? We added the intersection of A and B to the intersection of A and C to the intersection of B and C. And we saw that we counted everything here once except for the intersection of all 3, which was counted 3 times. So we need to subtract that off because we want a 0 there. So minus 3 times intersection of A, B, and C. And can we apply that to get the same answer? Well, let's see. What were these numbers? Would have been 15, 20, and 12. So let's add those up. 15 plus 20. Boy, if we don't get the right answer, something went wrong, right? Because it seems like it should be right. So 47 minus 3 times 9, intersection of all 3, and I get 20. What do you know? So a couple different ways of doing this one. All right, let's move along. Ooh, this one. Okay, so there were some questions asked on the discussion board for this one. So I think this one's difficult for 2 reasons. One reason is that the notation is hard for people to understand what the question's even asking. And 2, we have here a union of 4 sets. So we need to be able to apply the general principle of inclusion-exclusion to get a hold of this. Let's take care of that one real quick. So find this one. So general principle of inclusion-exclusion, I talked about in the video, but you follow the same pattern. We'll add all the singles in. Cardinality of all the singles. We'll subtract off the doubles. All right, I'm not going to draw all of these. How many of them are there? Well, how many ways are there to pick 2 sets from a set of 4 sets? Well, there's 4 choose 2 ways to do that. So we should get 6 of them here. 6 total here. I'm not going to write them, but we'll subtract all those off. And then we'll add in the intersection of any 3. How many should we get here? 4 choose 3, or just 4, so we'll get 4 total here. And then we'll subtract off the intersection of all 4. So you add, subtract. Each time you increase the number of sets you're taking the intersection of. And then what this is telling me, so the intersection of every I of these sets has 5 minus I elements, and that starts at 2. So the intersection of every 2 of these sets, A1 through A4, has 5 minus 2 elements. That means these intersections here, of which there are 6, each one of those, or let me just focus on this one. Each one of these is going to have 5 minus 2 elements, or 3 elements. So each one of these, there's 3 elements, and there are 6 total. And so this is going to contribute a, where do I want to put this? Let me put it over here. So this is going to contribute a minus 6 times 3. 6 total, each one had 3. The singles by themselves, right, these are 4 element sets. And so we'll start off with 4 times 4. So that's all of these added together, give me that. All of these added together, and it's negative, so negative 6 times 3. And then any 3 sets, so the intersection of 3 sets, so all the ones on this row, will have 5 minus 3 elements in them. So that's 2 elements in each one of those. 2 elements, and there's 4 of those. And so that should be a plus 2 times 4. And then here, the intersection of all 4, well, I works here between 2 and 4. So the intersection of every 4 sets has 5 minus 4, or 1 element. So this just has 1 element in it. And so that'll give me a minus 1. So add this up. 4 times 4 is 16, minus 18. That's a negative 2 plus 8. I'm at positive 6, minus 1. I get 5. Hopefully I did that correctly. If not, let me know. So there we go. All right, let's move on. All right, here's a fun one. So there's 2 ways we could go about this, either algebraically or combinatorially. Now, for an algebraic way to do this, this question was asked on the discussion board for this chapter, and someone gave a nice solution that shows the algebraic way to do this. So if you're dying to see an algebraic way to do this one, go ahead and take a look at the discussion board, find the question being asked, and see what they did to solve it. But what I'd like to show you here is a combinatorial way to do this. So I'm sure there are lots of questions of what exactly is a combinatorial argument, or questions like, I don't understand combinatorial arguments, which isn't really a question, but it's, nevertheless, I think it'd be good for you to see exactly what I mean by a combinatorial argument here, and how we can apply that to this. So I think this is easier than algebraically. So what I want to do is I want to count the same thing in 2 different ways. So on one hand, I want to count it like this. On the other hand, I want to count it like this. So this left side is really telling me what I'm counting. I have 2n, choose 2. So this is counting the number of 2 element subsets of a 2n element set. So I'm going to let S be a 2n element set. So I don't know, let me draw S. Here's S. There's 2n elements in here. Then the number of 2 element subsets is, well, it's 2n, choose 2, right? Sure. That's one way to count that. How else can we count the number of 2 element subsets? Well, what I'm going to do is I'm going to split S up. I'm going to partition it into 2 sets, into A and B. So I'm going to say let A, B be a partition of S into, I'm going to say equal sized sets. Equal sets. So that is, I have n elements in A, so the cardinality of A equals n, and the cardinality of B equals n. So I split S right down the middle. I know there's 2n, so it's even, so I can do that. I split it right down the middle in this partition, and I ask myself, what does a 2 element subset look like now in terms of A and B? Then any 2 element subset of S looks like one of the 3 possibilities below. So what are the possibilities? What could this 2 element set look like? Well, a 2 element subset of S, it could be an element of B and an element of A, right? That's a possibility. So an element of A and an element of B. And let's see, what else could happen? Well, I could have, say, 2 elements of B, or I could have 2 elements of A. And so those are my 2 other options here. So 2 elements of A, or it could be 2 elements of B. Notice that these are ors, right? These are 3 distinct possibilities that don't overlap. So if I know the number of elements that look like this, the number of elements that look like this, and the number of elements that look like this, I can add them all up to get the total number of 2 element subsets of S. So let's count how many ways there are to do each one of these. An element of A and an element of B. So procedure to generate this, pick an element of A, and then pick an element of B. Okay, so how many ways are there to pick an element of A? Well, there's n total elements in A, so there's n. How many ways to pick an element of B? Well, again, there's n total ways, so that's n times n, because that's a sequence of decisions, right? Pick an element of A and then pick an element of B. And so that is n squared ways to do that. How many ways to pick 2 elements from A? Well, A is an n element set, and we're picking two elements out of it, so that's n choose 2. How many ways to do it for B? Well, it's the same thing, right? A and B are interchangeable. And so adding these all together then, I get n squared plus 2 and choose 2. So this is equals total number of 2 element subsets of an 2n element set. But wait, we counted that before, didn't we? That was the same thing as 2n choose 2. Hence, 2n choose 2 is equal to n squared plus 2n choose 2. All right, you gotta admit, that's pretty sweet. This is what's a combinatorial argument. Understanding that there's multiple ways of doing the same problem. And what's great is we can take multiple ways of doing it, and since we're doing the same thing, the counts that we get in both cases should be exactly the same. So we get these great identities from that. So I do encourage you to look back at your activity for this chapter, back where I asked for combinatorial arguments, and see if you really did something like that, or maybe if something comes to your head now that you've seen this sort of an example. All right. Or not, I can't force you, but I think it's a good idea. All right, 8.5, number 8. Right, so we have, 8.5, number 8. We want to form a committee out of a group of 2 freshmen, 3 sophomores, 4 juniors, and 5 seniors. So in part A, we just want to know how many committees are there with no restrictions and with 4 students. So notice here, a committee, there's no special seats on the committee, right? There's not like a president and a secretary. No one's serving a different term than another person. They're all the same seat. Committee member is a committee member. There's no declination between those things. That's what tells us that this should be a combination, that there isn't an order to it. It doesn't matter who I pick as the first committee member, or the second committee member, or the third. They're all a committee member. And so this is, all right, total number of people is 2 plus 3, 5 plus 4 is 9, plus 5 is 14. So there's 14 total, so this would give me 14 choose 4 would be my answer there. And I'm going to leave it as that, and that's okay. You don't have to actually calculate these out. 14 choose 4. That is, that's the number. It's 14 choose 4. Exactly 1 student from each class. Okay. Well, let's think. Exactly 1 student from each class. So I need to pick a freshman, I need to pick a sophomore, I need to pick a junior, I need to pick a senior. So how many ways are there to pick a freshman? 2. How many ways to pick a sophomore? 3. Pick a junior? 4. How many ways to pick a senior? 5. So that's a total of, wait, do we know it's a 4-person committee? Give me a second. The committee must consist of 1 student from each class, right? Exactly 1 student from each class. And so this would be the right thing. We would pick a freshman, pick a sophomore, pick a junior, pick a senior. And so we get this. Notice it's not a combination because now there is, an inherent order in the way I'm doing this. I'm picking a freshman and then picking a sophomore and then picking a junior and then picking a senior. And when we look at the committee, we know there will be, right, one freshman, one sophomore, one junior, one senior. There is some difference between the committee seats. So 2 times 3 is 6, times 4 is 24. So we get, what, 120 here? 3 students from 3 different classes. At least the committee is to consist of 3 students from 3 different classes. All right, let's think for a second. All right, 3 students from 3 different classes. Well, what could the compositions of these committees look like when we're done? What does a committee look like? Well, it would either be 1 senior, 1 junior, 1 sophomore, or we could have 1 senior, 1 senior, 1 junior, 1 freshman. We could have, 1 junior, 1 sophomore, and 1 freshman. How many total ways are there? Did we get all of them? We have 4 classes, and we want to pick 3 classes from those 4. So that's 4, choose 3. We should get 4 for this. So I happen to be missing 1. So 1 senior, 1 junior, 1 sophomore, 1 senior, 1 junior, 1 freshman. How about a senior, sophomore, freshman? 1 senior, 1 sophomore, 1 freshman. Got it. There's all 4. And now in each one of these, I'm going to count how many ways are there to do that composition. So pick a senior, pick a junior, pick a sophomore. I got to remember, how many seniors are there? I'm going to zoom out so I can see that along with the work that I'm doing, so I don't have to keep zooming in and out. All right, so we've split any committee that looks like this, that satisfies this condition, 3 students from 3 different classes, into one of 4 varieties based on the composition in terms of class. And so now we can come up with a procedure for each one to figure out how many ways there are. So there's how many seniors? So there's 5 seniors. Pick a senior. There's 5 ways to do that. There's 4 ways to pick a junior. And there's 3 ways to pick a sophomore. So there's a total of, 60 ways to do that. All right, pick a senior, 5 of those. Pick a junior, 4 of those. And then pick a freshman. There's 2 of those. So that's 8. That's 40. I'm going to have to zoom out again. All right. 1 junior, 1 sophomore, 1 freshman. Well, to pick a junior, there's 4 ways to do that. Pick a sophomore, there's 3 ways. Pick a freshman, there's 2 ways. That's 6. There's 24 different committees that look like that. And then we have 1 senior. So there's 5 ways. Times 1 sophomore, 3 ways. Times 1 freshman, there's 2 ways for that. So there's 30 total here. And since, right, it could look like this, or this, or this, or that, we would add all of these up. 100, 124, 154. There you have it. So sometimes we need to split up our committees like this. So the things we're trying to make sure of here is that they're disjoint, right? So if my committee consists of a senior, a junior, and a sophomore, then it definitely won't consist of a senior, junior, and a freshman, right? Those are disjoint sets. And same for all 4 of those. So those are the things we're looking for as we move into this next problem, 8.5, number 10. So we just have seniors, juniors, and sophomores now, and we want to form a 4-person committee in each case. So if there's no restrictions, well, how many total people are there? 8, 12. This would be 12 choose. We want 4 people on the committee, so 12 choose 4. Again, there's no special seats on the committee. It's just everyone's a committee member. All right, at least 1 senior, 1 junior, and 1 sophomore must serve. So at least 1. So this gets tricky. A lot of people want to say, write it like this, where we pick a senior, pick a junior, pick a sophomore, and then pick someone that hasn't been picked yet. So pick someone that hasn't been picked yet. This would give us a total of 5 times 3 times 4 times how many are left over after I pick those 3? 9 are left over. This would give us a total of 15 times 4 times 9, 540. Problem with this is that you double count. There's actually committees that are counted, the same committee is counted twice if you do this sort of procedure. So let me try and illustrate that. So here's how I want to do that. So think of this like an algorithm for a computer, if you're computer inclined. So the procedure that someone would have invented here to do this, and this is a pretty common one. So if you thought of this, excellent, follow along with me. If not, do you see why someone might think of it like this? That might be a really nifty way to do it. So I'm going to try and convince you not to do it like that. That will get the wrong answer. So this is like a procedure, right? So first, step 1 will be pick a senior. Step 2 would be pick a junior. And then 3 would be pick a sophomore. And step 4 would be, all right, pick someone that hasn't been picked yet. Pick someone else. And so let's just run through that. So we have this list of 5 seniors, 3 juniors, and 4 sophomores. And so let's say, so our algorithm is going to go through and it's going to do this for every possibility. We want to know how many do we end up with? How many different possibilities are there when the computers run through this algorithm for every possibility? So I just want to focus in on a couple examples of what the computer might spit out. So it picks a senior. Let's say it picks the senior Abe. It picks a junior. Let's call the junior Jamie. Let's pick a sophomore, Sarah, maybe, and then pick someone else. So let's say it picks someone else and that someone else happens to be a senior. That's going to happen, right, at some point. Let's give a name to this person. Miranda. How would I pick such a long name? Miranda for that one. And again, so Miranda happens to be a senior. I mean, this is going to happen eventually with every other possibility. So that is going to happen. That is going to be one committee that comes out of this algorithm. Okay, and what's another instance of this algorithm? What else is it going to spit out? Well, let's say at some point it's going to pick the senior Miranda, right? And it's going to pick the junior Jamie. It's going to pick the sophomore Sarah. And what if it picks Abe? It will. Eventually, it will. It'll get to that possibility. It's going to pick Abe because that's someone that hasn't been picked yet already in that sequence. Well, so that's a problem, right? Because these are unordered sets. Because we don't care about who's on, what the place in the committee is. Everyone's a committee member. And so this committee is the same thing as this committee. Remember, sets don't have order to them. And that's what these combinations give us. And so this would overcount this one. And so what we could do is we could get further into the weeds in this and figure out exactly how many times the same committee is picked. We could figure that out, and then we could divide by that. If we know that every committee is picked twice, for instance, we could divide by 2. So we could go that route, but I'm going to show you an easier way that doesn't take us further into the weeds. What I'm going to do is I'm going to do it like how I did part C over here, is I'm going to split up what a committee might look like into some possibilities. So I'm going to organize the arbitrary committee by class type. So I'm going to call this committee compositions. So we know there's at least one senior, at least one junior, at least one sophomore. So we could have 2 seniors, right? And then 1 junior, and then 1 sophomore. That's possible. We could have 1 senior, 2 juniors, and 1 sophomore. Or finally, what's the last one? We could have 1 senior, 1 junior, and 2 sophomores. Since we have to have at least one of each, these are our only 3 possibilities. And each one of these is distinct from the other one and disjoint. In particular, it's disjoint from the other ones. That is, if a committee consists of 2 seniors, 1 junior, and 1 sophomore, it definitely doesn't consist of 1 senior, 2 juniors, and 1 sophomore. And so we're going to count how many ways are there to do this, how many ways to do this, how many ways to do this, and then add them up. So how many ways to pick 2 seniors out of 5 seniors? That's 5 choose 2. How many ways to pick the junior? Well, there's 3 juniors, and then there's 4 sophomores. So 5 choose 2 is 10, times 3 is 30, times 4 is 120. 1 senior, 1 junior, 1 sophomore. So there's 5 seniors, and then I have to pick 2 juniors out of 3, so that's 3 choose 2, or just 3. Times the sophomores, there's 4. So that's 12, that's 60. 1 senior, there's 5 ways to do that, times the 3 ways to pick a junior, and then 4 choose 2 ways to pick the sophomore, right? We have to pick the 2 sophomores. That's 6, and 5 is 30, so that's what, 90? It's 150, so 270 total committees that look like this. Hey, do you notice that this 270, so this is the right answer, that this 270 is half of 540? Turns out we actually didn't have to go that much farther in the weeds for this other method. That this sort of setup, the demonstration I gave you here, that these 2 committees are counted twice, or that this committee is counted twice, well, that's the total number of times it's ever going to be counted, because we would need these 2 slots to switch places, or these 2 to switch places, or these 2 to switch places. So each committee is actually counted exactly 2 times here. That's kind of difficult to see. It's harder to find that out than it is to just go through this kind of argument. But if we were able to see that every committee is counted exactly twice, have some kind of argument for why that should be true, then we can divide our 540 by 2 to get the 270 that is the actual answer. Pretty cool, pretty cool. Again, multiple ways to do it, multiple ways. All right, what if we want at least 3 seniors? At least 3 seniors? Well, why don't we try compositions again? So what are our possibilities? We could have 3 seniors, and it's just a 4-person committee, right? So we could have then 1 junior, or 3 seniors, 1 sophomore, right? Or 4 seniors. So there's 3 possibilities here. There's 5 total seniors, right? So this would be 5 choose 3 times the number of juniors. I believe there were 3 juniors. This would be the sophomores. 5 choose 3 times the number of sophomores. I believe there are 4 of them. And then times 5 choose 4. Again, these are all disjoint. This is a partition of the committees that look like this. So 5 choose 3 is 10. That's 30, 40, and 5 choose 4 is 5. So that's, what, 75. All right, how about at least 1 senior? If we want at least 1 senior. Well, this is like, again, this is like over, where did we do this? We did this in a previous one. I'm going to try and find it. Where we removed the ones. Oh, maybe we didn't. No, we definitely didn't do it there. Oh, how about over here? Yeah, at least, right, when we did this, at least 1 even digit back in this problem. Instead of counting all the different ways we could have 1 even digit in there, we just counted the number of ways, the number of codes that didn't have any even digits, and subtracted that from the total number of codes. So we're going to do the same thing over here. We already know the total number of committees, right? Where are we? Sorry, my Blackboard is lagging a bit. I think I might have too many tabs open. All right, at least 1 senior. So we know the total number of committees is 12 choose 4. And if we just want, so how about no seniors? So that would be, we would just be able to pick from sophomores and juniors. There were 3 juniors and 4 sophomores, so that's 7 total people. We want to pick a committee of size 4 out of that. So that would be 7 choose 4. And so the ones that aren't like that are the ones that have at least 1 senior in them. And so we'll take the 7 choose 4 and remove that from the total number of committees. And that's our answer. So part D, not too bad, as long as we think of things on the flip in terms of complements. Sometimes it's easier to count the complement than it is to count the set itself, and this is exactly what we're counting here is the complement. This is total number of committees, and this is just that set. All right, I think that's all of the ones I have for you. I'm sure that was a long video. I kind of get into it and lose track of time, but I think that's it. So I'm going to go ahead and end this and put some timestamps for when you can encounter certain parts. See you later.